Hello and welcome to the short summary of filters and regulators used in the DC power supplies. Filters are basically those circuits which are used to remove the undesirable AC quantities from the rectified output and reduce the ripples in the output voltage and current waveforms. There are many types of these filters, namely the capacitor filter, where a single capacitor is used always in parallel with the supply and the load resistance. And this capacitor filter is even called as the shunt capacitor filter. Next variety is this inductor filter, wherein a single inductor coil is used to filter the undesirable AC quantities by reaching the load resistance. This is called as even the choke filter. Next variety is the combination of inductor and the capacitor as the filter elements. Therefore, this is called as the LC filter, or the filter is even named as the choke input filter. And the last ultimate variety in the list is the CLC filter, and this filter is also named as the pi filter. Now we will see the working of the simple shunt capacitor filter. In the circuit arrangement, it is quite simple, wherein a single capacitor is used here. This is the only filtering circuit element of this network, wherein this circuit receives the output of the rectifier as the input, as seen in the waveform here, and the filtered quantity of this will be given as the output to this load resistance. Now, the V0 which is available across the load resistance is always equal to this voltage across the capacitor Vc. The characteristics of this capacitor is that it is having very good charging and discharging characteristics with its own time delay of the charging and discharging networks. Other than that, it is having its own opposition to the flow of AC and DC quantities through it, which is given by the equation Xc is equal to 1 divided by 2 pi Fc measured in ohms. And as this Xc, the capacitive reactance offered by this capacitor for the flow of the electrical quantity is inversely proportional to the frequency, it offers very low value of capacitive reactance, means the opposition for the AC quantities, and offers very high opposition for the DC quantities, as the frequency of DC quantities is very much low. When the lower value is in the denominator, the Xc value will be very much high. For a pure DC with frequency is equal to 0, Xc would be infinite. With these characteristics of the capacitor, this capacitor will be conducting majority of the AC quantities which is present in this rectified waveform, but it will not at all be conducting any of the DC quantities through this capacitor, so that most of the pure DC along with the unfiltered AC will be reaching this load resistance RL. Then beautiful charging and discharging characteristic property of this capacitor in this circuit is that it is having the zero time constant for the charging of the capacitor in this network, and it is having, while discharging, it discharges through this load resistance. That is why it would be having a very high discharge time constant. As the charging time constant of this capacitor is 0, it charges to the peak value as and when the voltage is applied. Along with the same line, the voltage of the capacitor rises up to this peak value, which can be named by some letter in the waveform. And the charging and discharging sequences can be seen by this green lines in the graph, wherein it charges suddenly instantly along with the applied voltage up to this peak. From this peak, it starts discharging through this load resistance. Due to the higher value of this load resistance, the discharge time constant will be very much high, and it slowly discharges from this peak value up to the lower value. By the time it reaches this point, again the next waveform, wherein is supplied by the input of the rectifier, will be charging the capacitor to the next peak value here. Now, the maximum value at which the capacitor is charged is called as the point A. If it is called as the point A, the lower point at which the capacitor drops to the minimum value, if it is named as the point B. From point A up to this point B, no diodes will be conducting in this circuit. Means all the diodes in the rectifier circuit will be not conducting. They will be reverse biased, and they will be not at all supplying the load resistance. And during this period from point A up to this point B, the voltage of this capacitor will be supplying the load current, and in supplying this load current, the voltage of the capacitor will be dropping to the lower value of this point B. Meanwhile, when the voltage of the rectifier output reaches and crosses this point B, again the next sequence diode will be forward biased after this point B and starts supplying the load current. With this supply of the load current by the rectifier diode, capacitor again charges to the next peak, and the same sequence of operation will be repeating in the subsequent cycles of the input. Due to this improved waveform of the capacitor filter, the ripples are reduced to the lower value from the point A up to this point B differences only. And this ripple factor is given by the formula RF is equal to 1 divided by 4 root 3 FC into RL. And the waveform which is given out from the circuit, from this capacitor filter circuit, is simply as shown in the figure now. And this shunt capacitor filter is very much suitable for the higher load resistance circuits, wherein it consumes very less load currents. The next circuit of the filter that we discuss is the CLC filter. This is even called as the pi filter. As discussed in the previous circuit, the capacitive reactance of these capacitors C1 and C2 will be having very low opposition for the AC quantities, and they will be offering very high resistance for this DC quantities. Coming to this inductor part L, which offers opposition to the flow of electrical quantities, and is given by the inductive reactance XL is equal to 2 pi FL, wherein the XL is directly proportional to the frequency of the input. For the higher frequency values, the XL will be very much high. That is, it offers very high opposition for the AC quantities, and it offers very lower opposition for the DC quantities. Now, with these characteristics of XC and XL, the first capacitor will be conducting the maximum of the AC quantities through it, and it will not at all be reaching the next part in this filter circuit, wherein the remaining AC characteristics and the DC characteristics will be passing through this inductor L. As this inductor will be offering very low resistance for the DC will be easily passing through this inductor, but this inductor will be blocking the AC. As the inductor used may not be the pure inductor, some of the AC characteristics will even be passing through this inductor, and those AC characteristics or the AC quantities which pass through this inductor will be again conducted through the lower resistance path of this C2. And this either the C1 or the C2 will not be allowing any DC quantities to pass through them, and the pure DC with a little bit of unfiltered AC quantities will be reaching the load resistance, and they produce the voltage V0 across this load resistance RL, as we can see the waveform in the wave diagram. From the wave diagram, it is so much clear that the ripples of this such an output is very much improved, means they are very much less in the magnitude. And with this reduced ripples, the ripple factor of this circuit is proved to be equal to square root on 2 divided by 8 omega cube C1 C2 L into RL. The advantage of this filter circuit is that it is having a superior filtering characteristic, but the voltage regulation characteristics of the both filter circuits are poor. These CLC or the pi filters are suitable for work in the communication networks, wherein the signals are regenerated at the receiving end. After this filter comes the block of this voltage regulator. Voltage regulator is a circuit which maintains a constant voltage across the load terminals irrespective of the changes in the supply voltage and the load resistance. There are many types of voltage regulators. Among these types of the voltage regulators, we will see the simple IC voltage regulator, which will be regulating the fixed positive and the fixed negative DC voltages. Among these fixed voltage regulators, we will see first the positive voltage regulator 7-8 series of ICs. These 7-8 series of ICs are the 3-terminal IC voltage regulators, wherein the pin number 1 is the positive input voltage terminal and the pin number 2 is the standard reference ground terminal, wherein it has to be supplied with the reference negative voltage in the circuit, and the terminal 3 is the positive constant voltage output terminal, which will be supplying the load here. In the connection, it is quite simple as shown in the circuit diagram. The capacitor C and C used at the output and the input terminals will be maintaining the stable voltages across those terminals. The fluctuating voltages from the filter circuit are input to this voltage regulator circuit, wherein this 7/8 series of the voltage regulator IC will be giving a very stable constant output voltage, DC output voltage, to the load circuit. This 7805 is one IC which maintains a constant plus 5 volts output across its output terminals, and the waveform would be like this as shown in the output waveform. Other varieties of these 7/8 series of ICs and their output voltage and the maximum and minimum input voltage ranges are presented here in this table for your reference. You can take the snapshot of this and note down all these things. Wherein this 7824, the last entry, will be making a constant, giving the constant output voltage of plus 24 volts with the minimum input voltage of 27 voltage and the maximum voltage of 38 volts only. And these ICs should be operated within this input voltage ranges to produce this stable output voltage at its output terminals. Similar to this 7/8 series, we have the next fixed negative voltage regulator, the 7/9 series of the IC voltage regulators. Similar 3-pin voltage regulator IC, wherein the pin number 1 will be the positive reference voltage terminal, even called as the ground terminal in this 7/9 series of ICs. Pin number 2 is the negative input voltage terminal, and pin number 3 is the negative stable DC output terminal, which will be supplying the load resistance here. In the connection, again it is simple as seen in the diagram, where the function of these capacitors at the input and output terminals are to maintain the stable voltage levels. With the fluctuating DC which is produced after the filter will be given as the input to this circuit between the plus and minus terminals here. After passing through this voltage regulator IC, the output produced and supplied to this load resistance would be having the constant negative voltages with no fluctuations in its magnitude. The 7905 IC used or shown in this diagram will be able to maintain a constant voltage of minus 5 volts DC across its output terminals. The same voltage will be available across the load resistance V0 with the mentioned polarity in the circuit. Different ICs of this 7/9 series are tabulated here for your reference, and note down the output voltage range and minimum voltage ranges are also mentioned here. The maximum voltage range can be referred from the previous table of 7/8 series, wherein the polarity would be minus here. With this brief summary, we will close the narration of the filters and voltage regulator circuits.